Good morning, I'm Diana Cafiso and I work for the Department of Applied Science and Technologies of the Politecnico di Torino. Today I'll tell you about a work developed with Drs. Irena Carmagnola and Drs. Annalisa Chiappone. The topic is the development of a natural-based hydrogel that is suitable for photopolymerization 3D printing and that has potential biomedical applications. Tissue engineering is a branch of biomedical engineering that uses cells and materials to repair or replace damaged biological tissues. It often uses cells seated in a scaffold. An ideal scaffold must mimic the 3D structure of natural tissue and must grant cells proliferation and survival in order to form new tissue. Recent studies in tissue engineering are focused on the development of technologies that are able to provide patient-specific scaffolds. In this context, 3D printing techniques combining with proper materials are able to easily produce cytocompatible and customizable scaffolds. Among the different 3D printing technologies, digital light processing (DLP) uses photopolymerization promoted by light irradiation to produce complex and high-resolution structures. However, the development of bio-based, biocompatible, and sustainable photocurable materials is fundamental to fully exploit these techniques in biomedical applications. Among the emerging materials for 3D printing, hydrogels are a class of soft materials that are able to absorb large amounts of water. In particular, natural polymers-based hydrogels have drawn broad interest due to their biocompatibility. Carboxymethil cellulose, CMC, is a water-soluble cellulose ether, which is biocompatible and therefore is an attractive natural polymer for tissue engineering and regenerative medicine. Light-assisted 3D printing requires functional groups that usually are metacrylic and acrylic groups. Therefore, in this work, carboxymethyl cellulose was metacrylated. The modification of CMC was confirmed by Farrell transform infrared spectroscopy and by proton nuclear magnetic resonance. The latter indicates that, as more than 50% of the carboxylate group present in the CMC have been effectively grafted with metacrylic groups. Hydrogels were prepared by adding a photoinitiator to 2% MCMC water solutions. Photoreological tests confirmed the photoreactivity of the functionalized material, the rapid reactivity, and the final elastic modulus of the cured hydrogel result suitable for DLP printing and similar to other printable bio-based materials proposed in the literature. Through the DLP 3D printer, hydrogels were formed in simple structures like cylinders as well as in more complex shapes. Samples were printed both with water-based solutions and culture medium-based ones. In this latter case, the dye present in the medium allows to obtain a better resolution. The 3D printed hydrogels appeared mechanically stable and flexible. Further tests demonstrated that these DLP 3D printed hydrogels possess promising mechanical and swelling properties. The printed hydrogels had a compressive modulus of 76 kPa. In addition, they were able to absorb up to 650% of water compared to the initial weight, without breaking or deforming, thus showing the great potential of this soft material. Finally, the preliminary cytotoxicity testing confirmed the biocompatibility of the studied formulations. Therefore, the goal of producing a new ink for DLP printing starting from lignocellulosic-based material was successfully achieved. A further possibility could be using cellulose-based fillers such as cellulose nanocrystals. This could allow to tune the mechanical properties of the hydrogels so as to resemble the properties of different tissues and to create, for example, patches for wound healing applications. Thank you for your attention.